This video lesson will take you through the highlights of dissolving and solubility. The objectives covered by this lesson will include 15E, 15F, 15L, 15M, and 15N. The notes that you need for this lesson can be found in your notes packet beginning on page 2. One of the most important things to understand about the dissolving of compounds is what happens on a molecular level when the water dissolves the compound. We're going to start here with a little animation of a process called solvation. Solvation is simply water molecules surrounding the dissolved particles. In particular, we're going to start by looking at an ionic compound. Here we have a crystal of some kind of ionic compound, maybe sodium chloride. In this little animation, the negative ions are blue and the positive ions are gray. I'm going to run this again, and I want you to notice that water, being a polar molecule, has a positively charged end pointed in the direction of the white hydrogen atoms. So these are the white hydrogen atoms on water. And water has a negatively charged end associated with this red oxygen atom. Notice that the gray particles, which are positive ions, end up surrounded by the partially negatively charged oxygen atom, and the blue particles, which are representing the negatively charged particles, get picked up by the water molecules with the partially positive hydrogen end pointed in. Here come some water molecules to take away a negatively charged particle, and then here are some taking away a positively charged particle. If we look up close at this negatively charged particle being solvated, you'll notice that the partially positive hydrogens on the water molecule surround the negative ion and pull it out of the crystal. Notice that dissolving takes place on the surface of the substance. If we look at a close-up view of a positive ion, here comes the partially negative charged end of the water molecules, and the partially negative oxygens surround the positive ion and pull it away from the crystal. And if we put the entire solution in motion, what you'll notice is that each individual ion is packaged up with a whole fleet of water molecules completely surrounding it. Every ion has its own set of water molecules and is free to move about independently. For this reason, solutions that have ions dissolved in them can conduct electricity because the positive ions and the negative ions are free to move independently of one another and carry the current through the solution. In more of a still frame picture, we have a little diagram here of the different steps of the solvation process. We have the partially negative end of the water molecule approaching the positive ion, the partially positive end of the water molecule approaching the negative ion. The cations get pulled away and surrounded by water molecules with the oxygen end pointing in. The negative ions get surrounded by water molecules with the partially positive hydrogen atoms pointing in. And here we have a positive ion and a negative ion that have been fully solvated by water molecules. You will be asked on your test to draw a picture of ions that have been solvated by water, so make sure that you understand this process. In class today, we did a demonstration called bright, dim, or nothing at all. And I got out the light bulb again, and I put some compounds into water and measured whether they were bright, dim, or nothing at all. Now, some of these weren't surprising at all. We've done them before. Nobody was surprised that sodium chloride made a bright light, or that sugar made no light at all, or even that sodium hydroxide with its metal and its polyatomic ion made a bright light. The more surprising thing was that HCl, which consists of two nonmetals, lit up our light bulb very, very brightly. And CH3COOH, which is made of a whole bunch of nonmetals, in fact, the very same elements as our C12H22O11, made for a dim light, as did our NH3, another combination of two nonmetals. So it became clear that while we have our original categories, ionic compound, and molecular compound, these three compounds that don't follow the rules, so we'll highlight the ones that didn't follow the rules. We didn't expect bright or dim or dim. These three compounds are going to require us to have a slightly new classification system, perhaps some additional classifications. When we talk about molecular compounds, we know how these dissolve. We remember our rule, like dissolves like, which means polar compounds can dissolve in water, nonpolar compounds cannot, because water is a polar compound. We know that when molecular compounds dissolve, they break into molecules when solvated, so these molecules aren't going to fall apart, and they don't conduct electricity when they're dissolved. This is an ethanol molecule right here, and when it becomes solvated by a water molecule, we simply develop a hydrogen bond between the hydrogen on the ethanol and the oxygen on the water molecule. One of the new categories we're going to need to explain some of our conductivity is the idea of the acids. Although our acids consist of nonmetals, they do have the unique characteristic that they increase the hydrogen ion concentration when they're dissolved. Because they give off hydrogen ions, acids are capable of conducting electricity when dissolved in water. We ended up with two acids in our collection when we did bright, dim, or nothing at all. The first one was hydrochloric acid. Hydrochloric acid is what we call a strong acid. Hydrochloric acid breaks up to form hydrogen ions and chloride ions, and all of the HCl that we put into solution falls apart into hydrogen ions and chloride ions. Our other acid that we had was ethanoic acid. Our ethanoic acid at first looks a little bit like a base because of the OH group, but it's this characteristic COOH that makes ethanoic acid an acid. The difference between hydrochloric acid, which can light things up very brightly, and ethanoic acid, which only makes a dim light, is that ethanoic acid is what we call a weak acid. In a weak acid, the vast majority of the particles remain together when they're put into solution, but a few of them, in this case about 5%, fall apart to make hydrogen ions and acetate ions. Our other category of compound that's opposite of acid is base. Bases are compounds that increase the hydroxide ion concentration when they're dissolved in water. Again, because of the conversation about ions, hydroxide ions, we expect bases to conduct electricity. Sodium hydroxide isn't a big surprise in terms of conducting electricity because it also happens to be an ionic compound. It falls apart to form sodium ions and hydroxide ions. The more surprising one was the NH3, or the ammonia molecule. The ammonia molecule is a base because the ammonia reacts with water to remove one of these hydrogen atoms and pull it over here, leaving behind some hydroxide ions. Now, while ammonia, NH3, doesn't have a hydroxide ion, ammonia does exactly what bases do. It increases the hydroxide ion concentration when dissolved because the NH3 tears apart the oxygen, leaving behind some OH-. Sodium hydroxide lit the light up very bright because it's a strong base. It falls apart completely. But again, the ammonia, much like our weak acid, doesn't fall apart too much at all. We're again looking at about a 95%, 5% split here on particles that remained together versus particles that reacted with the water. And then, of course, we have our ionic compounds. We've worked with ionic compounds quite a bit, but we may have misled you into thinking that all ionic compounds will dissolve in water. With ionic compounds, some of them dissolve, some of them don't. And we're going to need a fancy set of rules for determining which ones will dissolve and which ones will not. The solubility rules shown below are going to be given on your test. You just need to know how to use them. We do know that ionic compounds become ions when solvated, and they conduct electricity, or in other words, they're electrolytes. These solubility rules are going to help us determine which ionic compounds dissolve in water and which don't. These rules work like a hierarchy. You always start at the top and work your way down. As soon as you find a rule that works, you stop, use that rule, and don't look any further. Our rules here are that all acids are soluble. When you're looking for an acid, you're looking for something that starts with hydrogen or ends with this COOH group. And then we just proceed down from there. Almost all salts of sodium, potassium, and ammonium are soluble. Salt is just another word for ionic compound. And so on and so forth. If you need to use these rules to decide if something is going to dissolve in water or not, the key is to first take your item and break it into its ions. So I've taken each of these ionic compounds and I've broken it apart to look at what types of ions are present. Now I'm going to go to the top of my list of rules here. This one consists of sodium ions and chloride ions. So Rule 1 doesn't apply, but Rule 2 says almost all salts of sodium are soluble. Because of the sodium ion present here, sodium chloride is soluble or it dissolves in water. Next one is silver chloride. If I start working my way down, Rule 1 doesn't apply, Rule 2 doesn't apply, Rule 3 says all salts of chloride, we have that, are soluble except those with silver. That means that the silver chloride is insoluble and it's not going to dissolve in water. Our last one is iron hydroxide. We have iron ions and hydroxide ions. We end up having to go all the way down to rule number 7 before we find the hydroxide ion. And rule number 7 says hydroxide ions are insoluble except when they contain an ammonium ion or an alkali metal. Remember that the alkali metals are in the first column of your periodic table. That means that the iron 3 hydroxide is insoluble and it doesn't dissolve. If we were writing chemical equations, the solubility rules would help give us our physical states. Our sodium chloride, which dissolves in water, would be aqueous in a chemical reaction, whereas the silver chloride would be a solid, and the iron 3 hydroxide would be a solid when we're working with double replacement reactions. In the next video lesson, we're going to look at some double replacement reactions and how the solubility rules can help us determine which double replacement reactions happen and which ones do not.